Welcome to the SigFigs activity video. Before we talk about significant figures, we have to talk about exact and measured numbers. Exact numbers are numbers that contain no error. We encounter these in two situations. The first situation is when we count objects. So, an example of that would be if someone's holding two baseballs. They have exactly two baseballs. They don't have 2.1 or 1.99 baseballs. They have exactly two baseballs. The two places we encounter counted objects in chemistry are going to be subatomic particles, like protons within a carbon atom. A carbon atom contains exactly 6 protons, for example. And the other place we encounter them are going to be the coefficients in balanced chemical equations. We'll be talking about chemical equations in a future chapter. The other place that we have exact numbers is going to be when we are talking about the relationship between two different units in the same measurement system. So for example, within the US system, 1 foot is defined as containing exactly 12 inches. Or in the metric system, 1 kilogram is defined as containing exactly 1,000 grams. There's no error in these relationships. They are exact. Measured numbers are going to be any number that's not exact. So any number that's not counted objects or not a defined relationship within the same measurement system. Measured numbers are always going to involve some sort of measurement machine, and therefore they have some degree of error involved in them. So some measurement machines that we use in a chemistry class are going to be the balances or scales, graduated cylinders, sometimes clocks or stopwatches, rulers, things of that nature. These devices are never perfect though, so these measured numbers always have some degree of error associated with them. Let's identify some numbers as being either exact or measured. 824.75 centimeters is a measured number. How do we know this? Well, someone had to measure that length. The only way we could know that the length of an object was 824.75 centimeters would again be if we employed some sort of measurement tool, such as a ruler. In item number 2 right here, we have 23 students in a class. This is an example of an exact number. If we have 23 students in the class, there's exactly 23 students in the class. There can't be 23.1 or 22.9 students. There'd be exactly 23 students. These are counted objects. And then finally, number 3. This is also an example of an exact number because this is a defined relationship within the same measurement system. The definition of 1 meter is that it contains exactly 100 centimeters. Now you should pause this video and complete question number 1 in the activity. Once you finish question number 1 in the SigFigs activity, then resume the video. Welcome back. Let's talk about significant figures now. If we're given a measured number, we use significant figures as a way of determining or stating how accurate or inaccurate a number is. If a number is expressed to more significant figures, that means it's a more accurate measurement, a higher quality number. If it's expressed to fewer sig figs, that means it's less accurate and a lower quality number. So if we're given a number and we want to figure out how many significant digits are present or how many significant figures are present, here are the rules we use. All non-zero digits are going to be significant. So in the example of 234 grams, these are all non-zero digits, and therefore this number has 3 significant figures, these 3 digits right here. Zeros are more complicated. Sometimes zeros are significant and sometimes they are not. One time in which they are significant is when they're sandwiched between non-zero digits. In the example right here of 50,071, our zeros are sandwiched between non-zero digits, and that means this number is known to 5 significant figures. These sandwiched zeros are actually part of our number. The other time zeros are significant is when they're to the right of non-zero digits in a number containing a decimal point. So right here we have the value 50.00 meters. This is known to 4 significant figures because these zeros are to the right of a non-zero digit in a number with a decimal point. Zeros serve another role in our math system. Sometimes they're just present to show us the magnitude of the number, and they aren't actually part of the number. So if we look at places where this is the case, zeros are not significant when they're to the right of non-zero digits in a number without a decimal point. So in the example of 25,000 right here, these zeros are here to show us the magnitude, and our assumption is that this number has been rounded. It's not exactly 25,000. We only actually know it to 2 digits. Over here in the number 0.00479, we have only 3 significant figures. So zeros are also not significant when they're to the left of non-zero digits in a number with a decimal point. So these zeros here are not actually part of our number, they're merely present to show us the size or the magnitude of the number. Let's attempt to determine how many significant figures are in some numbers. In this number right here, 8,250, we actually have 3 significant digits present. We have 3 non-zero digits, and our 0 right here is to the right of non-zero digits in a decimal number, and therefore it is not significant. In our next number, 0.012 grams, we have only 2 significant figures present, the 1 and the 2. Our zeros out in front, again, are not significant. They're to the left of non-zero digits in a number with a decimal point, and therefore they're just here to show us magnitude. They aren't actually part of the number. In 8.20 right here, we have 3 significant figures. Our 0 is to the right of a non-zero digit in a number with a decimal point. So this 0 is indeed significant. And then finally, we have a number in scientific notation. We can use our rules about what types of zeros are significant, but a handy trick for scientific notation is all numbers in the coefficient, this number in front of the power of 10, all numbers in the coefficient are going to be significant. So this one's known to 4 significant figures. I'd like you to now pause this video and complete question number 2 on the significant figures activity. We are now going to talk about how to handle significant figures in calculations. We're going to talk about the rules for multiplication and division, as well as addition and subtraction. But before we do that, you have to be warned that your calculator is generally going to give you the wrong number of significant figures. Most often, it's going to report your answer to too many significant figures, and you're going to have to round away the extra ones. But sometimes, your calculator will also give you too few significant figures. Sometimes, if there's trailing zeros, zeros to the right of non-zero digits in a decimal number, your calculator may round those away. So be aware you might have to add those in. So we mentioned before that we might have to round off extra digits from our answer given by the calculator. We're going to use standard rounding rules here. The first digit that we're going to drop, if that digit is 4 or less, then we're going to simply keep the numbers out in front. If the first digit to be dropped is going to be a 5 or greater, then what we have to do is round up. When multiplying or dividing, we're going to use our measured number with the fewest number of sig figs to control our answer sig figs. So if we multiply together these two numbers, we have one higher quality number known to 4 significant figures and a lower quality number known to only 2 significant figures. Essentially, our lowest quality measured number in our calculation is going to limit our answer quality. So we can only know our answer to 2 significant figures here. Your calculator is going to spit out an answer of 5.304 or something similar to that, but we have to round it just 2 sig figs. The first digit we're dropping is 4 or lower. It's a 0 in this case, and so it just rounds to 5.3. We have a similar but slightly different rule that we use for adding and subtracting. We're going to limit our answer decimal places to the measured number with fewest decimal places in our calculation. So if we're adding together 25.2, which is known to 1 decimal place, and 1.34, which is known to 2 decimal places, our calculator will spit out an answer of 26.54. The problem here is we have no idea what comes after the 2 in the 25.2. It's known to just 3 significant figures. The hundredths place is not known, and consequently we can't know the hundredths place in our answer as well. The first digit we're dropping is this 4 right here, so we're going to round to 1 decimal place. And because this is 4 or lower, we're going to round to 26.5 is our final answer. So I'd like you to pause the video and complete questions 3 through 5 right now. Question 6 can be completed after the next activity, so save that one for later. Once you finish the worksheet, once you finish the SigFigs activity, go ahead and post in the discussion board.